Hello everyone. Welcome to day 4 of this FDP. So let's start. Can you please confirm? Is my screen visible? Am I audible?
Yes, sir.
Okay, thank you, ma'am. Okay, so in the last 3 days, uh, we have been discussing we have discussed many things, uh, starting with the idea of the foundations, the fundamentals, then uh, in lieu of those fundamentals, we move towards the idea of the unitary evolution that we see, the unitary transformation through the idea of single qubit and multi-qubit gates. And these unitary evolution through this unitary evolution through the gates is a very pivotal understanding of how anything works with regards to quantum computing. And yesterday we discussed on the lines of the proof of concept algorithms. Uh, so we discussed the idea of the oracle, first of all, that is the backbone or uh, the main engine of any algorithm. And then we some ideas, saw some ideas around the understanding of phase kickback. And this phase kickback is the major idea that exactly joins uh, the foundational understanding that we discussed earlier and the next frontiers that we discussed. Some of those frontiers we discussed yesterday, and the ideas that we will be discussing today and tomorrow. So the algorithms till this point that we had seen uh, have some specific requirements. So the understanding of last 3 days has been built on the idea of the quantum computers of future. That is when we have perfect fault tolerant machines that actually run the Shor's algorithm. Today we are coming back to the machines in which we actually have some they are that are noisy and small, and we are specifically asking that what can we do with them right now, and the answer to that is variational computing. And it's where most real quantum research is happening right now. So the algorithm that we discussed yesterday, that is Shor's and Grover's, are exact and provable. What we are saying, they are exact algorithms and they are provable, but they demand the error corrected qubits that if we do not have error corrected qubits, then it becomes somewhat problematic to handle them. And right now we don't simply have this idea of error corrected qubits. It is somewhat there is some uh, research, there is some discussion going on around having uh, error corrected qubits right now, but we do not have full error corrected qubit system like we need. And this is the area that we see. We are currently in the NISQ era, as we discussed. It was devised by John Preskill in 2018. Discussed, I think, yes, earlier. So we are focusing towards fault tolerant quantum computing, that is known as FTQC, fault tolerant quantum computing, in which we will be able to see Shor algorithm and Grover's algorithm in full flow. So there will be no problem. So today's methods run on today's noisy hardware. The hardware is noisy. It means there is some problem with the hardware. You get gargled data and many things. If there is even a small change due to some heat or temperature, anything, the system decoheres. And decoherence is specifically means that there now you will have to start from you will need to start again. And the one idea that unifies everything is the idea that we use quantum circuits with tunable knobs. It is like a knob. Plus, we also have a classical optimizer that turns those knobs. So we are actually moving towards some hybrid systems. That is, some part is done quantum mechanically and some part is done classically through some classical optimization techniques. And that single frameworks is what underlines the idea of quantum machine learning. And it comes back uh, on day 5, it is tomorrow, as variational quantum eigensolver and QAOA, that is quantum approximate optimization algorithm, if with in different applications. So we'll see that how it can be used. So uh, the focus today is to understand this variational loop, that what exactly is happening inside this loop. So the four parts for today. First is the foundation of QML, that why exactly are we interested in quantum machine learning, and the variational idea and the variational loop, what exactly is happening inside it. Part B is about the building blocks that actually build the system, the cost functions, very important idea, and the tricky business of getting classical data into a quantum circuit. That is what we that is known as encoding classical data. Very, you can say, important, and this is kind of utmost importance idea, important idea, because without this encoding, we can't move forward. The variational idea, the variational loop that we have, we can't even put one step forward. So without encoding the classical data. Part C is all about the actual models, where we will be seeing some classifiers, kernels, and the neural networks. And lastly, the part D is all about the hands-on lab, that how we can do this, uh, how we can bridge it towards day 5. So if you notice this, that this is less about famous algorithms and more about a method that we will be reusing, and just goes on a long way. Now, let's start the idea with the two different eras. So first era is about fault tolerant algorithms, and the second era is currently that we are in, that is narrational or NISQ algorithms. So let us draw this let us see this explicitly, that because it frames the whole day, the whole understanding of what exactly is happening. So era one that we are seeing, that it was about, it pertains to the idea that we discussed yesterday, that is fault tolerant algorithms with beautiful provable speed ups, but needing hardware that's years away. uh, Not that much, maybe 5 to 10 years, something like that, and it is continuously being updated. Whereas era 2 is variational, that is, we will see the what exactly we actually mean by variational, that how we can change the circuits mid measurement and many things like that. It is also NISQ, that is, uh, it is noisy, and it is uh, working at the intermediate scale quantum. Also, we understand it from a perspective that we are focusing on approximate solution, not exact solution. And the idea that we are using is it is heuristic. It is heuristic driven. It is so there might be no a general proof of advantage, but we need shallow and noise tolerant. It is shallow and noise tolerant enough to run on real devices now, whatever real devices we have. So the defining move of era 2 is at the bottom. That is a classical optimizer that trains a quantum circuit. This is what comes up inside the variational loop. Now, why to make this trade at all? First of all, why are we seeing this in the first place, that there are two different era? Because currently we give up the certainty and provable speedups in exchange for something that is running on present hardware. That is the central bargain of the NISC era. That is, era 1 will go a long way. It is promising the destination that we will be reaching sometime in some time. But era 2 is what you and your students ultimately can actually experiment with around you can say uh, till the point we are coming towards the idea of era 1. So it is not that one only era 1 matters or only era 2 matters. Both matter, but only one is hands-on today, and that is the era 2. So we are focused more on that how we can harness the ideas of era 2. Now, first of all, why quantum machine learning? Why exactly are we connecting the two fields, that is classical machine learning, and why are we moving towards the amalgamation of quantum computing with machine learning? Is because there is a hope. That is, a quantum circuit, as we know, it lives in an exponentially large space. So the hope is that maybe it can represent correlations that are hard classically. So this is what we are hoping towards. But the status currently is actually unproven. So there is no broad demonstrated advantage on real world data yet. So the question comes up that why would anyone would learn it, or faculties why should faculties teach it? So again, coming back to the same idea, that because it is where the most current NISC research and the projects that students can do actually sit, and it's a kind of a genuinely interesting reframing of what learning means. So we are moving towards the understanding that teach it as an active frontier and not a kind of a finished tool. We need to see it as an you can say a kind of a floating frontier or an active frontier that is going on, and see how we can cope up with it, and come to a understanding that okay, this is what we have now, and uh, as we continue this journey, this understanding, we will ultimately reach towards some idea of the exact provable algorithms. Now, the crux. This is the uh, concept everything else builds on, and how it starts with is that we take a circuit. We will first understand the what's the variational idea or an variational loop, and we'll try to see that how it uh, works uh, hands-on. What is the idea around it, and there will be some new introduction of some gates that are single qubit gates only, like the ry theta as we are seeing. Uh, it's a rotation gate, and we have these rotation gates in the on this single qubits only, that is poly by. If we have poly by gate, we will be seeing the rotation gate on it, so it will be rotation y, rotation x, and rotation z respectively. So what we start with is we take a circuit but leave some of its rotation angles adjustable so that we can uh, adjust it according to our data, or you can say accordingly, when we run it, we can change it. And as we the data comes up, we will move towards adjusting that, and we call them theta. These are the adjustable angles known as theta. So we run it, we measure, and the output is actually depending on those angles only, whatever angles we have started with, that is these adjustable angles. And as we do so, now we let a classical optimizer to tweak the angles to make the output better. That's what we actually uh, do in this second step. And the whole idea of this understanding, that is, first, choosing some angles, adjustable angles, with the idea of this parameterized quantum circuit. This parameterized means that we are using some parameters, and these parameters are actually the theta. And uh, the way we choose parameters in neural networks, and we will be connecting the idea of classical quantum neural networks with this idea of parameters. uh, the way we choose parameters in a classical neural network, uh, that is the weights and the biases, in very general terminology. So the same way here, we are focusing on this theta, that is the angle, and these are not just simple angle, that is that they are fixed, they are adjustable angles depending on how the data is actually stacked up. So the way we see it, that we are having some data, and depending on that data, the adjusting the gates are adjusted. So this is the crux, the first starting point. And then we have this optimizer, the classical optimizer, where we can use different techniques, whether they are gradient based techniques or gradient free techniques, that we will be discussing in a short while. And this classical optimizer will be actually making this theta, will be changing this theta, the parameter, to give us better outputs uh, by a particular measure. So that's it. This is the idea of that's a trainable circuit. And you will hear it called a variational circuit or an ansatz. That is, what is an ansatz? It is just a chosen circuit template, that we are specifically choosing some specific circuit, and this is what the idea of ansatz is. And crucially, it's shallow, which is exactly why it survives on noisy hardware. If we had some complex, some deep circuits, the problem is again the same thing, that in our noisy hardware, if we are handling some deep circuits, there is a risk of everything getting decohered. That is, the circuit might decoher in uh, you can say at any point. So this is why the variational idea is so much in prevalence, because of this having shallow architecture, that is, we can work around with only few layers. Now let us move towards the variational loop, that is this hybrid quantum classical idea. Here, exactly how it actually runs, the four steps, and it's worth saying them as a rhythm. That is, first, we start with the run the circuit on the quantum computer and measure it. That is, we are running this parameterized circuit with everything, and we are measuring it over different shots, many shots, whether just like we saw on the first day itself, the one shot versus many shots. So we run it for 1, 10, 100,000, depending on how the performance is coming out. Second, we compute a cost function, and this is a single number. saying it tells us that how good the result is, and if we are getting a lower number, that is it is better, because we are trying to find a cost function only. So we are trying to minimize the cost, whereas to maximize the, you can say, the effect of how this cost can be minimized. Whereas third idea is to hand it to a classical optimizer, as we just discussed, that which is proposing new angles. So this classical optimizer, just like we do in a neural network computing, we adjust the weights and biases, the parameters that are there in classical neural networks. We adjust the weights and biases. Likewise, we are focused on this idea of classical optimizer, which is actually going to propose some new angles. That is, we will be adjusting this theta only, and through this theta everything will be done. And lastly, the idea that is, we are repeating this, and we will repeat until the cost it stops improving. That is, we are or we get the convergence. So if you notice this beautiful division of labor, uh, the quantum machine is doing one thing it's uniquely good at. And what exactly is that? It is the idea of running the circuit, and giving us a good parameterization, that is depending on different angles. Whereas and we can specifically say that the idea of the unique understanding of quantum computing, quantum computer, is pertaining to the understanding of preparing hard to simulate states. So it is very important idea that simulating these states is quite a hard job. So this is what the quantum computer is actually focused on, whereas the classical machine is doing its part by optimizing the whole process. That is, whatever the results we get after measuring, after measurement, we will be getting a classical answer. So after that, we will be either doing some classification or regression or any other activity, and we will be applying some optimization techniques. So this whole understanding is, each part is playing its to its strength. This is what we are getting the just from this understanding, this whole loop. Now, what are the different uh, second, yeah, sorry, what are the different cost functions? Now, cost functions, uh, when we say, we are trying to unpack that what exactly this better means, because uh, from one perspective, better uh, might mean something, and from the some other perspective, from other frame of reference, it might mean something else. So let's try to unpack what is this better, because that's where the goal actually lives. The cost function is the problem, and it might be the classification error, or as we might see tomorrow, that it might be an energy of a molecule, when we will be discussing variational quantum eigensolver and many problems like that. So what exactly we are focusing, that this cost function is actual the is the whole problem actually, and we need to understand it from the context, whether it is a classification problem or a regression problem, a regression error, or an energy, you can say, ground energy of a system. Sorry. Yeah. So to minimize it, optimizers come in two flavors. That first one is the gradient based, where we use some techniques like gradient descent, and or some other variants of gradient descent, where we are trying to estimate the del cost by del theta. That is, we are depending with respect to this theta parameter, we are focusing on finding the cost, or we specifically see writes in some places del L by del theta. That is, L is specifically prioritized as for loss, that is loss function. So del cost by del theta or del L by del theta, same thing, nothing else. And this can be done using some parameter shift rule, that we are shifting the parameters. And this is one area which is estimating the cost, which is estimating how the cost changes with each angle. This is the gradient based technique. And another is the gradient free technique, like we have Kobaila or SPSA, some techniques like that, which uh, do not focus on on just finding the gradient of a system. They are focused on some statistical, you can say, techniques. So one honest idea around this is that every cost value is estimated from finite shots only. So whatever we will be finding, the cost is with respect to a number, or a finite countable number of shots. So it is noisy. It is noisy, and the optimizer is working with slightly fuzzy numbers. So this is what we actually need to see from an you can say real-time point of view. And notice the echo of earlier days, that it was to first of all guess the problem, that what exactly we are doing, then we measure the output, the states, and not output, measure the output, or sorry, measure the states, and then we adjust according to it. But the measurement taps the superposition and entanglement of model, classical model can't. So this is where a classical models lack, because they can't exploit measurement, superposition and entanglement. And this is actually done using the idea of measurement that is present in quantum computing only. So the first idea in this whole starting point, if you see the observe the understanding, where we start with is, it might seem easy to overlook. It is like a problem that's easy to overlook, but it is absolutely central. So what we are saying, that before a quantum model can learn from your data, from the data we have, that data has to become a quantum state first of all. So this is why we are saying that before a model can learn, it must enter the Hilbert space. Because without entering the Hilbert space, or as we say that without it, the classical data changing, becoming a quantum state, we can't do anything. And this step is one of the most often, you can say, important step that often dominates the cost. So sometimes the problem that we have with this idea, that is the challenge, is that we might end up shelling more resources than classical computing in this step only. So the question comes up, that what's the point if we are only shelling out some more resources than the classical computing in the first step itself, and after this we will be having some resources will be done. But the understanding is that there is certain advantage that we might get from this whole process. That is why we try to encode the classical data into qubits in as fewer resources as we can. And this is what we are focusing on. And this is actually a real limitation that comes back again and again. You might see it whenever we are discussing the idea of how to encode classical data in the terms of quantum, you can say, states. This first problem that will come up is the idea, or is this particular problem that is known as data loading bottleneck. We specifically say data loading bottleneck or state preparation problem. That is, to prepare the states, we encounter some specific limitation, we can say limitation, challenge with respect to the cost dominating and limiting the actual advantage. So the simplest, there are some approaches with respect to this, how this encoding is actually done, namely the angle encoding, basis encoding, and amplitude encoding. Now, uh, in angle encoding, this is kind of a simplest approach where each feature is actually becomes a rotation angle. And this feature, what this feature actually means, that is the data that we have. It is becoming a rotation angle, and we are using 1 qubit per feature. So this is the basic idea of angle encoding. And the idea that other idea that we have is of basis encoding, where we use bit strings to do some computational, you can say, to do some computation with these computational basis states. That is, we will be using uh, one values, or the 1 qubit per feature, same idea in basis encoding also. That is, there is no compressing mechanism in basis encoding as well as in angle encoding. So the basis encoding is very, you can say, very basic kind of idea, where we are, if we are given some data, like uh, we are given some 4 bits. So in turn, we will be using 4 qubits, and this is not that efficient. It is only, basis encoding is specifically used only for some toy problems, or if we have some very small data sets where we do not want to inculcate the idea of angle encoding or amplitude encoding, because it will again incur some cost. So this is where the basic encoding is like used. It is simple, but the idea is that it is uh, the challenge that we have currently is that getting numbers into Hilbert spaces isn't free. It is not just you can say simple idea that can be just done in a uh, in a second. So this needs quite you can say a good number of quite a generous amount of cost in is involved. Next that we have a very tempting option, that is the amplitude encoding, and this is kind of the most powerful uh, encoding technique among the 3 techniques. We have also one other kind of technique, but we are not focusing on that. That is phase encoding, and one is specific idea that has also propped up. We will see that also in a minute. So this amplitude encoding is the idea which packs like 2 raised to power n features into just n qubits. These n 2 raised to power n features are like packed into these amplitudes of n qubits. It is compact, and it wonderfully compacts the whole features, the whole 2 raised to power n features, and among the 3 features, among the three, sorry, encodings, this amplitude encoding has this capability of this compactness. Although it takes uh, a little bit of you can say complexity to handle this amplitude encoding. It is not a simple just mapping. One-to-one mapping can be done with respect to this amplitude encoding. So yeah, this is a little bit kind of a tedious process. Now, the catch in here is that preparing state can be very expensive. That's the particular catch in here. And sometimes wiping out the advantage, it wipes out the advantage that we were actually looking for. So the key point is that the encoding is the part of the it is a part of the model, and not a pre-processing afterthought. So if we make a feature map that is poor, then it wastes any quantum advantage that we might get. And this is what the idea of as I was iterating, known as the data loading bottleneck, or the uh, idea of uh, state preparation. And it is one of the, you can say, honest reasons why QML is quite hard. This is the basic understanding around this whole idea of uh, encoding techniques. Now, when we have this encodings prepared with us, we turn these encodings from a in the terms of an idea. It is not just a now a routine job. It is now being turned into an idea, and this idea is all about a feature map that is deliberately embedding our data into a rich high dimensional quantum state. And it is the quantum cousin of the kernel trick our ML colleagues, ML, you can say, techniques in just like support vector machine, they already know. So just like we use the idea of feature mapping in many different uh, algorithms in classical machine learning, the idea of a feature map with respect to a quantum feature map is very important to embed the data into a high dimensional quantum state. Now, in this whole understanding, we need to add some entangling layers as we go along, so that we can create correlations between features that a simple classical map might miss. So this is uh, a kind of you can say hope that is lovely, because data that is tangled and inseparable, it might classically it might become cleanly separable in this quantum space. So what exactly we mean by that we if we have some data that is inseparable in maybe two-dimensional space, and when we do some mapping, uh, the feature mapping, it might get separable, and in maybe some higher dimensional space when we do this along. So maybe I can show this quickly. Just a second. Connect my what we understand by this separable and inseparable data. So I'm showing in here so that everyone is able to understand this, at what exactly is happening with respect to this separable and inseparable data. Now, if in here we have some data points like this, and I do not have, I think, another ink, yeah, we can have. Uh, just take this blue. So this is data in original space. This is data in original space. When we apply some feature map, that is this phi, we might be able to separate the data in feature space. Okay, this is with respect to how a feature map can transform the data into a space where it is easy to process. That is how it is done classically. So we have these points in here and the other set of points, that is this blue in here. So now we have we can uh, draw a decision boundary, and this decision boundary will be able to separate the data quite easily. Whereas in here we were not able to do that in through you can say a single linear boundary. So it was not separable in here, but as soon as we do some we are doing some feature mapping, we are able to separate the data, and we are saying that this is the original space and this is the feature space. So the data is mapped onto some higher dimensional space. Now uh, visually we can't like see more than on paper we are able to see only two-dimensional view, so that is why I'm showing it like this only. But now uh, likewise in a you can say quantum perspective, how a variational circuit actually works. So we'll see the same thing. We have, I'll try to make it a little bit smaller because we have limited space in here. So we have one set of data, we have another set of data creeping it up. Now, what we are saying that pertaining to this, we are having some set of points like this, where this is some point x and this is y. Now, what can be done in a variational circuit? So this is a variational circuit. What exactly are we doing? We are mapping this. We are mapping this through some feature mapping technique, that is phi, and we are using the idea of uh, the different rotational understanding gates, where we have this states on which we apply these rotational gates ryx, ryx. So we should be z, not x, because we want different data points. Also, we should put this as z so as to have a different points. So this x corresponding to this ryx and z corresponding to ryz, and on these we have actually applied the operation. And what's this operation? That is phi. Let me write it in here. What's this operation actually? It's phi, the state x, z, that is the get. So this is what is actually being done in here. Now, what is this transformation? The idea in here is just like we were mapping in classical way, that we were mapping our data into some higher dimensional space through the feature map. We are in here processing our data through this feature map only. And what's this feature map saying? That we have the data and this is being mapped to this F, where the vector space F is actually a Hilbert space. It is becoming now a Hilbert space, and this Hilbert space and the feature vectors that we have are the quantum states. And what are the feature vectors? These x and z. These are the feature vectors are corresponding to them. So this is giving us a transformation from x to of x. This is how the transformation, if you see this, we had x, we moved towards phi of x comma z. This is corresponding to this x and z. I hope everyone is understanding what exactly this transformation is actually all about. Transforms x to phi of x, and this is being done using what? A unitary transformation, that is u phi x. And this is the whole idea of a variational circuit whose parameters depend on the input data. And what was the input data in here? It is x and z only. So this is the idea with respect to this variational circuit. Now I am writing in here variational circuit discussed in previous slide, so that everyone is able to refer to it, that what exactly is happening, and they're not getting confused, because we didn't have space in here, so we have done it in the previous slide. Okay, so as we were discussing about the entangling layer in here, that we need to have some entangled layers, and this actually gives us the separable data. So the idea is that uh, if the feature map is easy to simulate classically, then we have actually gained nothing, because if it can be done classically, then why was the need of the quantum space? So usefulness actually requires hard to simulate maps. That is where the quantum computing will actually come into play. It is not just the gimmick that okay, we can simulate it classically. So yeah, this is the comparison with respect to the classical way and the quantum way. And let me do one thing, make a distinction so everyone is able to see this. Let's move towards the this workflow. Let's assemble the pieces into one picture. This flow is the whole session. This whole session in a single diagram. That is, we encode the data through a feature map. That's just we saw. Then process it with the variational circuit. And this is when we say that how we are developing a variational circuit, this is what we actually did for a particular circuit. And how what exactly this variational circuit consists of. There are three specific things that actually one is written in here, that is measure and the compute cost. So variational circuit, as we saw, as we see, it is black. Let us change the So variational circuit. So you can say it as adaptable quantum circuits. Okay. And first step is to prepare a fixed initial state. This is the first point in the understanding of a variational or parameterized quantum circuit. So we say either VQC, that is variational quantum circuit, or PQC, parameterized quantum circuit. Both of them are used in that particular sense. Although PQC is one part of variational quantum circuits, we have many other things in variational quantum circuits, that is VQCs, variational circuits. So we prepare a fixed initial state. That is the first thing. That is the kind of a zero state. Just like we have been doing earlier also. It can be a vacuum state also, that we have nothing. We have nothing. We have just a zero state. And second is to have a quantum circuit, build a quantum circuit. That is U theta. And this is parameterized by a set of free parameters. Theta. Now, what are these free parameters? I hope everyone remembers some idea of that. We used to say that this is a free radical. That is like we have a a free molecule of maybe uh, gas or anything like that, and we say that, oh, this is a kind of free radical, or any material. So like that, we have some analogically, we have one free parameter, but we have free parameters, and these free parameters can be adjusted. That is why we are saying that this is an adaptable quantum circuit, that we can adapt it accordingly, that how this free parameter is actually going to run. And lastly, the third thing, it is measurement of an observable B at the output. So what is this B? It is like an observable unit that we need to get the output of, and this observable, this observable, this can be maybe made up from local observables. So this can be done from you can say some local observables, so as to get a particular measurement across the system. So this is the basic idea around variational circuits. And the variational circuits, they are trained by a classical optimization algorithm that makes queries to the quantum device. Now, we saw the first part, that is the encoding, then the process with a parameterized or the variational circuit, in which we are processing it with a variational circuit, measuring the system, and then we measure the system, then we compute the cost, then we optimize, and this optimization is will be done classically. So we optimize the angles, and then we repeat. So this is the whole work to end to we can say end to end workflow. So now when you trace it once with your understanding that what exactly is happening. It is just the variational loop from a few slides when we were discussing. So the idea that we were just discussing in here, the variational loop, it's the same thing. It is packaged in a different way. That we run the parameterized circuit, we compute and measure, and then we do some classical optimization, and then we repeat. So this is the actual workflow. This is kind of a workflow. This is why we are differing it in that particular sense. That this both of them are kind of a same thing. So if you can redraw this, you can say the whole chain from memory, that you can think that you have actually understood what exactly this means. So the QML workflow, also we have two practical modes to distinguish. One is the training and the other is inference. And this is the caveat. This is the idea in classical machine learning also, that we do some training and inference like this. So training is what we have just described, that is adjust the angles on labeled examples until predictions match. This is what we do specifically in training. Whereas inference is different and it is much cheaper. That is, we freeze the angles, some specific angles, and then encode a new input. Then we run it once and read the prediction with that. So what exactly is the difference? We are freezing the angles at the starting, and here is a kind of a mental model to understand them, so you can understand it, that the whole thing is the understanding that we have starting from this is that the whole idea is just a kind of a mental map, uh, a kind of a quantum circuit, uh, and it is playing the role of a trainable model where the encoding and the answers together are its architecture, and just like we have the different layers in a neural net. So in a way, we have the input layer, the hidden layers, and the output layer. uh, Likewise, we have the idea of this different layers in here. What exactly is happening? We have encoding, then variational layer, then entanglement layer, and we measure. So in a basic sense, this is the idea that we actually use in here, that we do some encoding, we do some we add some variational layer to it, we and then add some entanglement layer, and then we measure it. We can have some more ideas inside it, but this is the basic idea around the understanding of a QML workflow. Now, we will discuss some more ideas in a few minutes. I think the XLR team needs to discuss something important, and then we will continue our discussion about this variational quantum classifier and what are the quantum kernel methods, the quantum neural networks, the challenges and limitations, and specifically the parent plateaus, and then we'll see the hands-on part of this. So yeah, I think Shushmita, I think you want to intervene.
Yeah, yes, sir. We'll take for 15 to 20 minutes. Then
Yeah,
you can continue with the class.
sure, ma'am.
Yeah, thank
So
you.
please do not leave anyone. We'll continue after the discussion by the XLR team, and we'll see that what needs to, what more is coming up your way. You can continue.
Yeah.
Yeah,
Thank you,
okay,
sir.
sir. Sheetal, over to you.
Yeah. Thank you, Sushmita. Good afternoon to all the faculties and the professors who have joined in here. So I hope my screen is visible to everyone.
Yeah, yes.
Okay, thank you. So yeah, I have joined the session around 5 minutes back and I found it very interesting. So I won't take a long time. I have joined in here today for a quick discussion in your support as in terms of placement, where you support your students and directing them towards interview or guiding them on how to prepare themselves for the job opportunities in partnering IT company. So as we can see here, we have the faculty development student placement nominated drive, where we connect your top students with direct interview opportunities at partner IT companies. So this initiative, it is from XLR exclusively for students who are deserving enough to guide them from classroom to corporate interviews. So what we expect from the faculty is that they rightly identify the deserving students and help us to know each other so we can help them in cracking interviews. So let me give you a quick walkthrough. The core objective, XLR would want the faculties who have joined in here to identify their deserving students, connect them to the hiring companies. At the same time, we also support employability through CSR linked hiring, offering fresher packages ranging from 4 to 9 lakh per annum. So this is not a mass hiring. It's only for students who have been chosen by the faculty themselves. And this initiative helps strengthen the industry academia bridge while recognizing and rewarding high performing students. So how we are going to do this? Firstly, we would want to identify the performing students from your colleges who have strong communication skills, willing to take interviews, and also students who show foundational technical knowledge or the ability to learn quickly. In short, we are looking to nominate high potential students who are ready to step into the industry. So these are the benefits the students will be availing through this initiative. Firstly, they will get direct interview opportunities with the partner IT companies with the packages ranging from 4 to 9 lakh per annum. Additionally, students also gain valuable industry exposure, resume validation, and real interview experience. We also provide extra support like assessment, test, resume, review, and interview readiness session. So this is how our selection and interview flow would look like. It starts with the initial screening by XLR based on their skills and role fit through different assessment, whether they are fit for the role. So the students will be screened based on their technical knowledge, whether they are aligned with the role, their communication readiness, and many more aspects. Followed by which the students that get screened or clear the first level will receive interview invites and preparation resources from the XLR team. Then XLR will introduce the students to the partner IT companies and they will undergo the interview rounds, that is technical and the HR rounds. Once the student clears these rounds, they would be offered with a job offer and this would be shared directly with the student themselves. So to ensure the students are well prepared, XLR additionally provides pre-interview training. They review the resume and provide interview tips for the nominated students, coordinate with partner recruitment and support, and at the end, they share the feedback on the student performance and the areas of improvement so that in the future, they can crack other interviews. So this initiative is a part of our CSR activity and we believe that employability is responsibility. So today, we request the faculties who have joined in here to scan the QR code and fill in the details, or you can even drop us a mail to ftp.placements@xlr.com. For those deserving students, and from there on, XLR would connect with those students and help them in the job interview process. So we will be holding the screen for another 2 to 3 minutes. The interested faculties whom you want your students to grow in the future and outshine can scan the QR code or any queries also, if you want, you can just drop it by scanning, and our team will be getting in touch with you. So I hope the faculties who have joined in here and who are interested, they have scanned the QR code. So thank you for your time and support, and we look forward to your nominations and helping your students achieve their successful careers. So that's all from my end. Happy learning. Keshan sir, you can actually proceed. Thank you.
Okay, so let's resume from where we left off. So we were discussing this QML workflow, and as we discussed the idea, that the whole idea, the encoding the variational understanding, variational circuit, and the entanglement layer, and how do we measure it. Now let's take a look into this, into a new type of canonical model, and it is just the workflow that makes this concrete, that the whole what's the whole understanding. So feature map that we have, it is used to encode our input. First of all, that's what we started with. Next, we have a variational answers with trainable angles. Now, what's this answers? As we discussed, if you see this again, we were discussing on the lines of how anything can be adjusted uh, using a particular template, that is a chosen circuit template. That is what the second last point, you can see the answers. This is what actually powers the idea of how this feature map can, first of all, needs to encode the input, and these trainable angles can be used to actually adjust the model according to the parameter. that what's the different parameters and how those parameters, that is the theta in here. The parameters in quantum variational quantum classifier or circuits is the theta. How these rotation angles can be you can say updated, and this follows a measurement, and that becomes our predicted label. That is whatever we get from the measurement. Based on that, we now are able to do this. We are able to do some prediction label, and this prediction label is actually what a classical part is. We are doing that classically, whether something is X or Y or Z or anything like that. So training minimizes classification error by tuning the theta in the loop itself. What we are saying, that training is minimizing this classification error by the tuning matrix, tuning idea, that we tune the theta in the loop itself. This is somewhat closer to the idea of hyperparameter tuning we do in classical machine learning, whether it is we are using some random search technique or grid search technique or any other technique like that, which is used to tune the hyperparameters. And specifically, in from a classical point of view, we in neural networks, we tune our learning rate, and how learning rate will actually help. This is the or will actually take us towards the an optimal solution. That's a very, very important point, because if we take learning rate too less, it might not converge, or you can say not we should not say it might not converge. It will do very slow learning, and it will take some time. If we take a higher learning rate, it will go into it can go into oblivion. It can like miss the actual optimal solution, and the balanced learning rate, this is what we are actually every time striving for, that it is also not too slow and not too you can say quick to you can say uh, get to the optimal solution. So the idea we have is that the problems that we encounter in real life are are a part of non-convex optimization, because in convex optimization, when we say this, idea, just like we have a general idea, that is this is a kind of a convex uh, uh, layer where we the local, one second, let me use a different thing. The local and the global solution, or the local optima point, are somewhat same. Local equals to global. But in the case of non-convex optimization, this is convex, but with respect to non-convex, where we might have some different type of system, where we are not the system might just stop here, thinking that okay, it started from here, and it has found some local you can say optima, but actually this solution is not the correct solution when we have some you can say function, non-convex function like this, because we know that we are seeing visually that this point will be our you can say correct optimal solution. Because so the problem that lies with respect to this convex optimization and non-convex not convex function and non-convex function is that in a convex function we have the local and the global minima as our it will be almost same, but in non-convex function there is a possibility that our first local solution is not actually the optimal solution. There might be some other global solution. This is a global optima that is actually our optimal solution. So this is one important aspect. And also you might see a stretch, this stretch where there is actually no training happening, or you can say it is just a steady movement where there will be no training or very limited amount of training that is going to happen here. This we will be discussing, and this actually refers to the idea of barren plateau, that is very significant, pivotal part of where the learning can like come to a standstill. So the analogy that helps in retrospect, uh, that we can think of the variational circuit as a trainable neural network layer, but instead of the neurons it has, so its neurons are like the entangled qubit operations and not just weighted sums. So when we see from a neural network point of view, we generally just do the weighted sum idea that okay, y is equal to wx plus b, where w is the weight, x is the our the input, that is the neurons, and the b is the bias, and we are getting some output with respect to. So this is not the case in from quantum, you can say classifier point of view, that is variational quantum classifier. We are not doing the weighted sums. We are focused on entangled qubit operations, and that's the model uh, uh, the everyone can run in the lab shortly. So you can understand that how this trainable neural network actually runs. Then we have a different way to use the quantum computer, and this is the quantum kernel methods. So this is a contrast that we can use differently. So instead of training the circuit, we use the quantum device only to measure the similarity. So what we are focusing on, that we are not going to train the circuit. In this understanding, we are just going to measure the similarity. And what this similarity actually means, that what's the overlap between two data points in the feature state. So uh, the similarity metrics that we or the overlap that we built is an idea that is innate to the understanding of quantum computing, that comes from the idea of inner products, or can say dot product. So when we if you remember from the first day's discussion, when we had something like this, that 0 and 0, when we are trying to see the similarity between the states, it comes out to be 1. Whereas if we try to see the similarity between 0 state and 1 state, it comes out to be 0. And why so? Let's see this briefly. 0 and 0. If we are saying that this is 1 0 and this will be 1 0, so we will take the this as the whole column vector. This is the column vector. We will be taking this in the terms of column vector and the row vector. So I'm just writing it as it is. So 1.1 and 0.0, so it will be coming out to be 1. That is 1.1 plus 0.0, because it is just a dot product only. So let me write it fully so that everyone can understand this. Let's write this correctly. So 0.0 gives us 1. Whereas with respect to the 0 and 1, we will be getting the answer as 0 because of the dot product 1 0 and 0 1. So it will lead to 1.0 plus 0.1, that is 0. So the idea of having similar, you can say similar vectors or the orthogonal vectors, that is the perpendicular vectors, that comes up in the understanding of quantum kernel methods. So this overlap is actually computed on a hardware, and then completely ordinary classical support vector machine does the actual classification, that is this SVM. So as we apply the overlap, that is this overlap between states psi x and psi x dash, the square of it. So when we see this overlap, it is giving us some estimate on hardware, and we are able to do the classification of it using some classical technique like the support vector machine. So notice the contrast with the idea of variational quantum classifier we just saw. What's the contrast? The idea that we are seeing in here is that here are you can say there are no trainable parameters on the circuit. First of all, that's the understanding, and the quantum part that is actually computing the similarities. And because the idea of inner product, as I am saying again and again, it is innate to the idea of quantum computing. So quantum part is actually computing the similarities, and the learning is being done classically. Also, one thing I would like to write for everyone to understand is that Hilbert space. Keep this in mind. I should have like discussed this earlier also, but Hilbert space is actually equal to saying vector spaces plus inner products. And that is why when we say that the idea of why the idea of inner products is you can say innate to the idea of quantum computing, it is because the Hilbert space is actually combining this property, that is vector space plus inner products. And we have been discussing this right from the start, that the idea of this amplitudes and encoding, that is before we are saying that the model is able to learn, we must ensure that it is entering the Hilbert space, and that is why the idea of this inner product is so profound from quantum mechanical point of view. So the idea why this quantum kernel method is studied is because the theory is quite clean, a very cleaner idea is there, and it's clearer when a quantum kernel could actually win. Because if we are able to get the overlaps quite easily, and it is able, we are able to distinguish in that sense, we can say that okay, these quantum kernels can actually surpass the classical kernels. So this is why the idea of quantum kernel methods is quite important. Now, very uh, broader, from we'll see this from a broader point of view, very important idea, that let us place all of the understandings, all of the discussion that we have seen till this point in its broader family. And what is that? That is the quantum neural network. So this is the crux of the whole idea that we have discussed till this point. A quantum neural network is what? It is just a parameterized quantum circuit that is trained like a neural network. And the variational quantum circuit classifier, that VQC that we just met, is one of the simplest examples of it. So the structure that we have seen, it even rhymes with the classical networks. And how it is so? Because we start with the trainable rotations that we have, that is the layers of rotations that are trainable. We start with them. They play the role of weights, just as we have the parameters, the weight parameter in classical neural network through the layers, when we start from input layer towards the hidden layer and go towards the output layer. Whereas the entangling gates, they play the role of connections. So they are mirroring the connections, the weights and the connections, just as we see in a neural network. So for instance, we have this simple neural network where we have this inputs, we have these hidden layers and the output layer. So when we put these connections to place, what exactly this means, that how each layer is connected, and what exactly is this signifying. So it becomes a little bit messy when we like put all the connections. That is why we uh, try to use some uh, dropping techniques, that we drop the layers. So yeah, it becomes a messy, but no issues. The idea is that this is input layer, all these three are hidden layers, and this is the output layer. So the connections that we have built up throughout this particular network, we are able to understand this from a point of view that entangling gates are actually playing the role of these connections. But don't let the analogy oversell it, that we are not trying to oversell this idea, because the computation is actually being done with the amplitudes and entanglement and not real valued activations, just as we have in in classical neural networks. So uh, this system, this whole network might seem like very good until unless you come to know that uh, we can make some smaller or is a simpler network, but the whole crux of this particular network is that using the activation functions that actually introduce the nonlinearity. So, and what exactly this nonlinearity means, that we are able to handle complex relationships, just as we right now we are seeing some complex relationships, although I told you that I am not good at drawing and I have messed it up a little bit, but yeah. So we are able to handle complex relationships between these hidden layers, this first, second and third layers of hidden layers. And uh, this is where the activation functions come in. But in the quantum counterpart, we are actually doing this using just the amplitudes and the entanglement, and it is still an active research area. So we do not need to, like, just as we said, that we do not need to oversell it. It's just in motion, it is going all along. And next, we move towards the idea that how expressive and how trainable these are, and from a point of view that what exactly are the challenges with it, with regards to it. So the this is now the time for an honest reckoning, that uh, uh, you understand very clearly, and please do not like skip this in any way. If you like go towards it at the in some at some later time, this is the most important understanding of why there are some problems with respect to the current the era 2 that we have been discussing. What are the problems? Uh, and this actually what makes us credible in the longer standing, that what are the problems and how we are able to handle them. So data loading, as we discussed, that data loading can cost as much as any advantage we had gained. So that's one of the important problem, you can say challenging problem that we had seen with respect to the encoding the classical data. Next, and this is the, you can say, the holy grail of the problems of the problems. So that is the idea of parent plateaus that I just tried to show in here, that the training can like get stagnated for what's the idea is that the training can stall entirely. It can stall in its entirety. So gradients might vanish exponentially, and that is the vanishing gradient problem. We also have exploding gradient, but it is somewhat you can say handle it using gradient clipping and many techniques. But the problem of vanishing gradient is somewhat a very you can say challenging. And a little bit digression for 1 minute, so as to make you understand why exactly is this important. Because the problem, the gradient vanishing problem, sorry, the vanishing gradient problem, this was the problem that actually affected the sequence models, that is we see in natural language processing, NLP, the models that have been used, the deep learning models, whether it is an RNN or LSTM or GRUs. So this idea, the problem of vanishing gradient, it affected these models quite a bit, and we tried to overcome with this with the understanding of some techniques like attention mechanism, where we were able to handle long range dependencies, and uh, uh, the vanishing gradients would be maybe handled using some techniques to like attention to handle these long range dependencies, so as to uh, uh, get a better understanding of this sequential processing. But uh, there were far more problems in the sense that the long range dependencies that we see were conceptually they were implicable, they were okay, but when we actually practically did the application, it was not possible. So that is why the idea of the fundamental paper that came in 2017, attention is all you need, that is the where we implemented the transformer uh, uh, system, that is new way of handling the you can say this mod problem, came up with the self attention mechanism, and that was the you can say breaking ground for the idea of LLMs, the large language models like ChatGPT, Claude, and Gemini we see today. So we have come a long way in the last these 8 to 9 years after the introduction of this paper, that is attention is all you need, and uh, we have been able to solve many problems regarding that, but there are others still many problems with respect to um, the the problems that we were seeing earlier, specifically the vanishing gradient problem. And the parent plateaus is still a substantial problem. It is not a problem that has been solved. So it is a kind of a central open problem. So yeah, I just wanted to digress for 1 or 2 minutes so that you can connect it with the understanding that what is happening in the AI, Gen AI, and agentic AI space, and how it is actually corroborating with the idea of quantum computing in current space, and how we can cope up as faculties. Everyone can cope up with the idea of connecting the this AI boom, specifically I would say Gen AI and agentic AI boom. AI boom has been there, so Gen AI, agentic AI boom with the idea of this quantum computing, the sudden leverage and sudden surge has been there in the idea of how going towards quantum computing. Now, another problem that is there, that noise corrupts everything, and worse, as circuits deepens. So it worsens as we move towards some we can say complex circuits or deep circuits. So this is one another problem. Also, every cost evaluation needs many shots. So training is sample hungry. That is, we need quite a bit of you can say sample or data. And the bottom line is that for real world classical data sets, no clear general quantum win has been shown as till this point. Say so. Uh, the idea is that you need to we need to understand that there is a certain promise as well as there are some limitations also that have been there. So we can't just go very high and mighty with the promises. Also, we can't be just boggled down that okay, oh, these are so many problems, so how are we going to proceed? It is not like that. And no one is waiting for you that okay, maybe we will when these problems will be solved, then we will hop in, and then you will be left behind. So that is what the idea is. So briefly, the idea of barren plateaus, and this is like the single most important obstacle as we discussed. So let's try to understand it properly, what exactly it is. So as a circuit gets large and expressive, its cost landscape goes almost completely flat. That is, gradients shrink exponentially, and this is what the vanishing gradient problem is. So picture it like trying to find the bottom of a valley on a surface with no slope anywhere. Now, what exactly we will be doing? That if we want to find the point on the surface of a valley of a surface, where we have no slope, we need no scope of seeing any slope. So the optimizer has no idea that which way it has to step, and the training just stalls because it is not understanding that where it should go. So there are active mitigations, that is we can do some mitigation techniques. How we can mitigate it, that we might start with some smarter starting points. That is one area, that is smart initializations. We can use some problem tailored and SaaS, just as we discussed, that we can use some circuit template. But the problem is tailored for a specific idea, that is for maybe problem related to drug discovery. It is different from for a problem related to chemistry, drug interactions. There is a different idea, and many things like that. For maybe a cost optimization problem, that is a different understanding. So we can also use shallow circuits for that. But here is the deep tension that actually governs, that actually overshadows it, is the more expressive we make a circuit, the harder it often is to train it. So this is the a kind of a trade-off, just as we have a kind of a trade-off, not just for an analogy, we have a trade-off in bias versus variance trade-off in classical machine learning, that if we increase the bias and we decrease the variance, we get underfitting. If we let the bias is less, variance is high, we get overfitting. If both of them are high, then the system is itself is very problematic, and we want less bias and less variance. So likewise, we need to understand that if we want some expressibility, that is, we want more expressive models, it becomes more difficult to train, and the very powerful circuits will be enough to be interesting, but they are also prone to plateaus. So good QML design actually balances the expressibility and trainability rather than maximizing either. And this is the same idea that we try to entertain in the idea of bias versus variance trade-off. We do not want overfitting or underfitting with the two ideas. We also don't want high bias and high variance. We want low bias and low variance, in the sense that we want to make a kind of an optimal a point of view. Although we won't get low bias or low variance every time. We want in the curve that we see, that generally we see for bias variance trade-off, we try to make up a boundary where we are actually focusing on moving towards an optimization point. So this is the whole idea with respect to the uh, you can say the parent plateaus. Now let us move towards today I have tried to take hands-on lab a little bit lesser on a lesser side, because the idea, the whole idea of variational circuits is actually very uh, consuming. It is very powerful, and directly deep diving into the hands-on lab would not have served the purpose. So the what we will be trying to see a kind of a variational quantum classifier where for a two-feature data set, and we will try to and do some encoding training and how see that is how the decision improves. Then we will see one quantum kernel classifier, and we try to we vary the feature map, and then for the entanglement, and also try to observe the effect. And we'll be doing this on from the Qiskit platform only. One important idea that is there, that we will be doing this on the from the point of view that on using on the simulator. No hardware is used in here, so we will be just seeing it from a simulator point of view. So let us move towards the idea of this variational quantum classifier, and what exactly is the understanding with respect to these why this variational quantum computing actually matters to us. I hope my screen is visible to everyone. Uh, me maximize it a little. Okay. Second. Okay, I think it is this much only. Now, the understand flow that we have is the setup. That is the first point that we have done. Then the data set, we have taken the two feature, two class data set, just this. Then we have the encoding process, the data encoding. So we we have encoded one data point using this data encoding, oh sorry, angle encoding. Then we have the idea of model, building the model. So we have built a model, and how this model has built. This is the main major idea where there will be a prediction being done. So we have used a feature map. This is the feature map. This is a feature map, and the answers that is entangled in it. That is the expectation. We have used this entanglement answers in that particular sense. That is uh, just a you can say makeshift feature. Then we have the cost and the cost curve, that how the cost is actually evolving, and then it is deep diving. So this is the variational loop with the cost curve, and see this, it started with a good promise, then it is falling, and then it is flattening. That is going into in the range that we see it like the barren plateau. But this is what we want. This is not a understanding of plan plateau. It is like we just wanted to flatten it, so that we are seeing the change with respect to the training. What's the training process? Then we have the entanglement, that is we are evaluating and seeing the quantum kernels and the barren plateaus. So step by step, we are just seeing first of all, we are seeing just the overview that what exactly is being done, and then we'll move on to the idea. So we do the entangling layer. We apply the entangling layer. We are specifically using the gradient-free method. We can use gradient-based method also, but it requires then a whole lot of training and all, and it takes I can say quite a bit of time. So I'll show you one way how to do that using the same platform, that a Qniverse that we were seeing yesterday. And then after entangling, we do the quantum kernel. This is the other way to do the idea. That is, it focuses on similarity. So till this point, we had seen what the idea is the idea with respect to the quantum classifier, variational quantum classifier. This tells us the idea of a quantum kernel where we are focusing on the similarity in the matrix and the accuracy that is coming up with respect to that, because we had taken same points. Then why the QML is hard, and the barren plateau effect. If you see the result or the variance that it tells us that the shrinking trend that we have seen, it is the barren plateau. That is, if we have a bigger, you can say, number in the terms of these qubits, it might it is not meaning that automatically it is trainable. It is not like that. And then reading the results. So let us just try to first understand what is happening step by step. So first of all, the setup, very basic idea. We have nothing, just the NumPy library, the matplotlib, and the other libraries like the quantum circuit and the parameter vector. Also, we have the sparse polymetrics. That is, we will be, as we are handling the sparse data sets only, that is 2x2 data sets, 2-bit data set. So that is why we are just using sparse polymetrics. And second point, that we have the tiny 2-feature 2-class data set. So if you see in here that we have taken two features, that is A and B, and this A and B is like we are just getting the labeling them as a class -1 and +1. That is what exactly is specifically focused on, that we are dividing the data set in the sense that the 0.25 and 0.2520 values we are seeing in here, and the randomness that is being involved in with respect to 0.06, and we are actually using this as our training data to make the shift from how this training data will be now encoded. So as we get the training data, we encode one data point, that is using the angle data encoding. And this is where we say that the actual data, that is the classical data, it is becoming like a rotation angle on its own qubit, and it is entering the Hilbert space. This is visible in this particular sense in the RY gate also. If we say this, if we apply RY gate in here, if you see it here, right now we are just in the 0 qubit. Putting RY qubit on this, if you see, it is having what angle? Right now the theta rotation angle is pi/2, that is 90 degree. And if you see in here, in pi/2, if we have this pi/2 theta angle, it is going into a superposition. Just like Hadamard puts the qubit in the qubits, single qubit into superposition, this RY gate, that is the rotation Y gate, that is whether it is in here, Lossish sphere. I don't think RY gate, we have RY gates in here. No, we do not have. Yes, okay. Let us come back to this. We do not have the RY gate in the Bloch sphere. Otherwise, we can see that in that place also. So you can see the Q sphere, just the idea that what exactly is happening. Nothing, no change is happening. The understanding is that the amplitudes with respect to these state vectors are what? If you see 0.707, and the phase angle 0. The phase angle that is coming out to be is 0, because of that understanding, that cos pi/2 plus sin pi/2. So in that I sin pi/2. So in that particular understanding, we are getting it as a 0. So not just the cos pi/2, it will be changing with respect to that. So this is what RY gate actually does. And a very brief understanding of what these rotation operators are all about. We have three different operations: Rx theta, Ry theta, and Rz theta. And the expression that we are seeing, cos x plus I sine x. So A, that is one of the three polymatrices, that is the Rx polymatrix, or the Ry polymatrix, or the Rz polymatrix. This is the these three gates are with respect to the poly X, poly I, and poly Z matrices that we had seen for one single qubit gate. And this is the idea with respect to the different rotation operators. Now, the Ry theta, when we are applying this that is 2. We are taking theta as theta by 2, or sorry, pi by 2. So in that case, we are getting a superposition state. And when we get back in the terms of this code, what exactly is happening with respect to it is, sorry, this, yeah, what is happening with respect to this is we are applying this ry onto this x0, that is the first data point, that is the x, this is x0 with respect to that, the a and b that we had defined, and the ry with respect to this x1. And this is actually giving us the values, that is r by 0.311 and r by 0.68386 with respect to the points, the values that we have in here, 0.25 and 0.75. So when this is done, now this data, the classical data has entered the Hilbert space. This is the first understanding of how encoding, we can encode the data point. Then the model, the important, the main, the crux, the what exactly is happening. We have taken 2 qubits, that is perfectly okay. We have taken theta as the parameter vector, that is we are taking a parameterized vector. We this theta and the number of qubits that we have will be adjusted, adapted. And if you see the whole circuitry, what exactly it starts with, that you have the encoded data that we have already done. So it will be, we will be fetching the value from there. We have the trainable layer, that is one first trainable layer. Then we have the entangling layer, and then we have the trainable second trainable layer. So what exactly this trainable layer is all about is varying the theta, that how we can vary the theta with respect to this data point. So if in here, why I just wanted to show you this, because now I am going to change the theta, and this is what the optimization is all about. I am going to change the theta, that is instead of pi by 2, I am not going to write it as pi by 4, and see the change that is going to happen in here. The amplitudes have changed, that is 0.924 and 0.383, and this the probability is also has also changed. If before that, if you see, the probability was like what, 50% probability of 0 and 50% probability of 1. That was a probability, but amplitude, as we you can say do the squaring of that, it gets us the value 0.707 and 0.707. But as we change it, if you see, the probabilities also have changed, and the amplitudes pertaining to have changed. But if you see specifically probability, that is 85.35 and 14.64, the amplitudes will not be like that, because amplitudes are the squared value of that. So what's the understanding with this, that as we change the theta, that is this rotation, we will get new solutions to that. And this is the idea with respect to this feature map, that is the prediction. This is the prediction. Then we have the cost function. What's the cost function is all about, that we are just doing, the cost function is all about the understanding uh, between the actual and the predicted value. So whatever the actual value we have and the predicted value, the difference between them, we want to minimize that as possible, as less as possible. Then the variational loop, and variational loop we have specifically used the Cobila method. So this is the gradient free method. Gradient based methods are somewhat expensive to handle. And now the understanding is that we are starting with random parameters. This is what one of the idea also was, to handle the parent values and many problems like that. And the final training cost that we are seeing with respect to this function, that x train y train that we had earlier used, is that this variational loop is first starting with a promising idea, then it is the cost is falling down, and then it is flattening. So this is what we are actually striving for, how the cost should flatten out. Then we are evaluating and testing the effect of this entangling layer, the layer that we use after the training, you can say training layer, that is this is specifically trainable layer. And we have many variations to it, that we have trainable layer, then entangling layer, then trainable layer, then entangling layer, and this goes on for a long bit of time. Then as we get the test accuracy with respect to with entanglement and without entanglement, we are getting almost the same value somewhat. So the quantum kernel that we saw earlier, that the idea is that we want to find the similarity, and the understanding in here is to find this phi of xi and phi of xj, that is the inner product, and this is what the inner product is all about. We are finding the inner product between two particular you can say kernel values, that xi and xj's. So it is coming out to be, text accuracy is coming out to be 1.0 for this, because we are classifying this point on average, that is it is similar to, so it is dependency free. And lastly, why QML is hard. So the interpretation of this is that when we do some parameter shift, that is depending on the parameters, we are shifting it one bit by bit. We might see some parent plateau effect. So the understanding is that we are getting the gradient variance very it is changing very rapidly, and this is what the idea is all about. The gradient is like is coming to such position that we are not able, the system is not able to, the point is not able to understand where it should go, because it is getting confusing, that there is no slope at all. So this is the idea of parent plateau. And lastly, the reading the results is simple, that we have the how we can train the parameters. So this is what I wanted to discuss for today. I hope everyone has at least understood the basic pipeline. I'm not like uh, hoping that everyone will get the code or anything like that hands on in one go. I myself haven't I do not expect this, that it took me also some time to understand what exactly is happening. So I'm hoping everyone is has at least understood the basic idea of what exactly is the pipeline and how to handle the workflow. And if there are any questions, please do let me know. Otherwise we can like close out the session and look forward to the last day of the FDP, that is tomorrow, with some future directions and all. If there are any questions, do let me know. Okay. Ma'am, I think we can close our session. If there are any questions, maybe they can discuss later.
Yeah, sure, sir. Thank you. We'll wind up. Thank you.
Okay. Thank you. Looking forward to tomorrow's session.